Hi everyone, welcome back. In this lesson, we'll cover confidence intervals, prediction intervals, and added variable plots. This chapter builds directly on the t-test, so make sure you're comfortable with the t-statistic and hypothesis testing before diving in. Let's start with confidence intervals for regression coefficients. A confidence interval is a range of values derived from sample data that is likely to contain the true value of an unknown population parameter. It quantifies how uncertain we are about our estimate. For example, a 95% confidence interval means if we took many samples and computed a confidence interval from each one, about 95% of those intervals would contain the true parameter. Imagine, the true value of beta 1 is represented by the dashed line, and each time we take a new sample, we compute a confidence interval. If we take 20 different samples, theoretically, 19 out of 20, or 95%, should capture the true parameter. There is an important duality between confidence intervals and two-sided hypothesis tests. If a hypothesized value falls outside the confidence interval, the null hypothesis will be rejected at the corresponding significance level. In terms of formulas, for simple linear regression, a 1 minus alpha % confidence interval for the slope beta 1 is beta hat 1 plus or minus the critical value t times the standard error of beta hat 1. Beta hat 1 is the estimated slope, dot t is the critical value from the t-distribution table, and the standard error measures the precision of our slope estimate. If the interval does not contain 0, it suggests a significant linear relationship between x and y. For multiple linear regression with p predictors, the confidence interval for the jth coefficient generalizes naturally. Replace beta hat 1 with beta hat j, and replace n-2 with n-p plus 1 degrees of freedom. In simple linear regression, degrees of freedom is n-2 because we estimate two parameters. In multiple linear regression with p predictors, we estimate p plus 1 parameters, one for each predictor plus the intercept, so the degrees of freedom become n minus quantity p plus 1. Before we talk about prediction intervals, let's introduce the concept of prediction, or using our model to estimate the response for new observations. Suppose we have a new set of predictor values, x star. The true response, y star, follows the same regression model with its own random error, epsilon star. For the least squares point predictor, we simply plug the new x star values into the estimated regression equation and replace each unknown beta with its estimate. For simple linear regression with one predictor, this reduces to y hat star equals beta hat 0 plus beta hat 1 times x star. The prediction error, the difference between the true y star and our predicted value, equals the estimation error in our regression coefficients plus the random error epsilon star from the new observation itself. The estimation error captures how far our estimated coefficients are from the true coefficients, evaluated at x star. But epsilon star, the random deviation for the new observation, is irreducible. No matter how large our sample, there will always be some inherent randomness in the new observation. Under our standard regression assumptions, the prediction error is approximately normally distributed. This allows us to construct a prediction interval. Now that we understand prediction error, let's construct a prediction interval. A 1 minus alpha % prediction interval for y star is given by this equation. Y hat star is the point predictor introduced in the previous section. The critical t-value is the same as in the confidence interval for the coefficients. And SE pred is the standard error of the prediction. This is the term that is most different from the standard error term in a confidence interval, and is the reason why prediction intervals are wider than confidence intervals. In matrix notation, the standard error of the prediction is given by the formula on the screen, where S is the residual standard error, lowercase x star is the vector of new predictor values, and uppercase X is the matrix of predictor values from the sample. Since matrix notation is rarely tested on the exam, it's unlikely the exam will ask you to apply this formula, so a conceptual understanding of this formula is sufficient. For simple linear regression with one predictor variable, this simplifies to the square root of MSE times the quantity 1 plus 1 over n plus the squared distance of x star from the sample mean divided by the total variation in x. Notice the predictions become less precise the further x star is from x bar. The key difference between a prediction interval and a confidence interval for the mean response is the extra 1 inside the square root. This extra term accounts for the irreducible variability of the new observation itself, making the prediction interval always wider than the confidence interval. For predictions to be valid, the new observation should follow the same model as the training data. For example, using a model developed with data from regions with populations up to 40,000 to predict for a region with a population of 400,000 would be ill-advised. In this last section, we cover added variable plots, also known as partial regression plots. An added variable plot reveals the marginal relationship between the response and a single predictor, after removing the linear impact of all the other predictors. This lets us see the unique contribution of each variable. To build an added variable plot for predictor xj, we first regress y on all predictors except xj and save the residuals. Next, we regress xj on all those other predictors and save those residuals as well. Then, we plot the results from the first set of residuals against the second set of residuals. Here is an example with 4 predictor variables. Each panel plots the response residuals against the residuals for one predictor. A steep, tight pattern, like x1, indicates a strong, unique contribution, while a flat, diffuse cloud, like x3, suggests that predictor adds little after accounting for the others. The slope of the regression line in each panel equals the corresponding beta hat from the full multiple regression. This makes added variable plots a powerful way to visualize the role of every predictor at once. Added variable plots can also visually reveal nonlinear relationships that might otherwise be missed. In this example, the plot indicates that x4 may have a quadratic relationship with y. The partial correlation coefficient between y and xj, controlling for all other predictors, can be computed directly as a function of the t-statistic for b sub j. The t-statistic for b sub j tells us how many standard errors the coefficient is from 0 in the full regression. A larger absolute t-statistic produces a larger partial correlation, indicating a stronger, unique relationship with y. A key advantage of this formula is efficiency. All partial correlation coefficients can be computed from a single multiple regression output, without needing to run separate regressions for each predictor. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.